Okay guys, so it's time to answer one more important question about this chapter, and that is, what is space complexity? By definition, space complexity is a way of measuring how much memory your algorithm needs to execute according to the input size. Just as performance, memory is super important. If the memory that your algorithm needs is larger than the available memory, then sacrificing performance might be needed in order to reduce the memory complexity. Just like we do with time complexity, we measure the space complexity of an algorithm using the big O analysis. If you remember, the time complexity depends on the number of fundamental operations that our algorithm executes. And these fundamental operations were simple operations just like addition, subtraction, product, division, assignment, bitwise operations, the return inside functions, and comparisons. Very similar, the space complexity depends on the number of primitives that our algorithm stores. And let's see what are these primitives. They are booleans, characters, integers, floats, pointers, references, and so on and so forth. This is all the theory that you need to know about space complexity. Now let's start analyzing some examples. First one is the first algorithm from the time complexity. What are the primitives used here? The variable which stores the sum, and the integer I which iterates through every value between 1 and n. So our algorithm uses only two primitives, meaning that the space complexity is constant, or using big O notation, big O of 1. As the second example, we will analyze selection sort. What are the primitives used here? First of all, the indices I and j, the min index variable, and more than that, an array A which contains n integers. Because of this array, we say that the space complexity is big O of n. But you should know that there is one more notion, which is the extra space complexity, which consists of only the memory that we use and not the one that is provided in the input. In this example, the array A is given in the input, and all the extra memory that we use are these three integers. And this is exactly why we say that the extra space complexity is big O of 1. Now for the third example, we will use a collection that stores the memory dynamically. In C++, we call it the vector. In Python, it is the list. In JavaScript, array. And in Java, array list. Let's say we are given a positive integer n and we want to store its divisors into a vector. What we can do is have a variable I iterate through each value between 1 and sqrt of n. Check if I is a divisor. If so, push value I into the vector of divisors. And then push also the value n divided by I only if it is different than I. In order to find the space complexity of this algorithm, we should ask ourselves how many elements are being pushed into the vector of divisors. As you can see, we perform two pushes of I and of n divided by I, and we perform them inside the for loop, which makes at most sqrt of n iterations. So the total number of primitives this vector is going to be populated with is 2 crossed sqrt of n. As you can see, we don't take into account the variable I, as it is only 1 and we ignore constants in space and time complexities. And this is exactly why the space complexity of this algorithm is big O of sqrt of n. Now for the fourth example, let's store the edges of some graph. Let's say the graph has n nodes and m edges. Using my favorite language, which is C++, we can store these edges in a vector of vectors of integers. I know this might sound a little bit complicated, but if you think about it, for each node we need to store a list of integers, where each integer represents a neighbor of that node. And because we need to store n lists, we will basically store a list of lists, which is the vector of integers. Now let's say we have defined a function add edge of x and y, which adds the edge x and y each time an edge is given. In order to do that, we push the value y into the list of x's neighbors and push the value x into the list of y's neighbors. Now let's think about it. What is the space complexity of this algorithm? For each edge, we are pushing two more primitives into some lists. And because we have exactly m edges, we will have exactly 2 crossed m integers. And we might be tempted to say that, okay, that's it, the space complexity is big O of m. But it's not. That is because we also store a list for each of these n nodes. And the list is represented as a pointer to the head of that list. So our algorithm stores 2 crossed m integers and n pointers, thus resulting in a space complexity of big O of n plus m. For the fifth example, let's have an array A of size n, and let's have its content poured into a hash table. And let me tell you how. Let's say we have a hash table, index of value, which will store for each value the index of the element that has that value. How many primitives does this algorithm store? We might be tempted to say n, but that's not true. For each new assignment, a hash table actually stores a pair consisting of the key, which is a of I, and the value, which is I. So there are 2 integers. This doesn't change the overall space complexity, but it's nice to know. And in conclusion, the space complexity of this algorithm is big O of n. I can't wait to see you on the next lesson, in which we will practice some more space complexity analysis.